The first talk is going to be given by Ana, Medero, and Garrote, if I'm not wrong. The speaker is Ana, I think. Okay. And the title is a Monte Carlo procedure based on the use of copulas for risk assessment of dam overtopping. 15 minutes are allowed, questions included. Please.
Thank you very much. I'm from the Technical University of Madrid in Spain, and I'm going to introduce the study called a Monte Carlo procedure based on the use of copulas for risk assessment of dam overtopping. And the focus of this study is to compare the probability of occurrence of a flood event with the return period linked to the risk to the dam. The presentation structure is divided into 5 sections: an introduction, the proposed methodology, the case study, and finally results and conclusions. A flood event can be characterized by the peak, volume, and duration. So, a multivariate frequency analysis is needed to study the probability of occurrence of a flood event. In the case of the bivariate case, these associated joint return period curves are easily obtained by means of a copula model. However, the return period is the time elapsed between two successive events exceeding a threshold. So, as the hydrological risk to the dam is related to the maximum water level reached, that threshold needs to be defined in terms of maximum water level elevation, instead of only in terms of probability of occurrence of a flood event. The maximum water level reached depends on 2 factors: the full hydrograph, which is defined by the peak, volume, and duration and shape variables, and the dam characteristics, such as the spillway length, the fluid control volume, and the operating rules. So, different events with different variables values can reach the same water level when they are routed through the reservoir. These events will have the same risk to the dam and will be located in the same return period curve. So, in the present study, both kinds of return period curves are analyzed in the bivariate case of the peak and volume space. In the figure, the black curve would represent the probability of occurrence of a flood event, and the purple one would represent the risk to the dam. The proposed methodology begins with the selection of the copula that represents the dependence structure between variables better. Then, a set of synthetic pairs are generated by the fitted copula, and a set of observed hydrographs are used to ascribe a shape to the synthetic hydrographs that are generated. These hydrographs are then routed through the reservoir, and maximum water level reach is estimated. Then the associated curves, the return period curves related to the risk to the dam, are obtained. At the same time, joint return period curves via the selected copula are obtained. And finally, both kinds of return period curves are compared. The case study is the Santillana Reservoir, which is located in the central west of Spain. The drainage area is over 300 square kilometers. The reservoir volume is 82 cubic hectometers, and the capacity of the uncontrolled spillway is 300 cubic meters per second. The observed data consists of pairs of maximum annual fluid peak and fluid volume, and the univariate marginal distributions for both variables are the Gumbel distributions. The first step in the copula selection is the dependence evaluation of the observed data. Then graphical analysis and non-parametric run-based dependence measures such as Kendall-Stowe or Solomon Row, is estimated, and both kinds of tools result in a positive association between peak and volume. Well, the second step in the copula selection is the copula's parameter estimation. Then the copulas firstly considered are cut down via the Kendall-Stowe volume, and the parameter of the remaining copulas is estimated by a two rank-based methods, the inversion of Kendall-Stowe method and the maximum pseudo-likelihood method. And now a set of synthetic pairs are generated by the studied copulas. Well, now a goodness of fit test is needed to evaluate what is the best copula model. So a first notion is given by the graphical tools. Then the scatter plot of the observed data and the sample generated by the studied copulas is shown. It can be seen as some copulas like Gumbel, Galambos and Hustler fit worse the largest observation. And Clayton copula generate more scatter values in this area. So overall, it seems Frank copula seems to be the best copula model, but it has to be verified by a formal test. So Kramer-Von-Mises statistic based on the empirical copula, and p-values are estimated for each of the studied copulas. The lowest value of the statistic with an appropriate p-value is the Frank copula, which is parameter obtained by the method of inversion Kendall-Stowe. Then this is the selected copula. In figure, observed data, a generated sample, and level curves of the Frank copula are shown. Now, by the fitted copula, a set of 100,000 synthetic pairs peak and volume are generated, and a set of observed hydrographs are used to ascribe a shape to the synthetic hydrographs that are generated. The procedure is the following. The ratio of peak to volume is obtained by each of the observed hydrographs and for a synthetic pair. Then they are compared and the shape of the closed hydrograph is selected. Then the shape is rescaled using the peak value. When the synthetic hydrographs are generated, they are routed through the reservoir, and frequency curve of the maximum water level reach is obtained. Then the return period linked to the risk to the dam, which is the inverse of the probability of occurrence of the probability of exceeding a water level, is associated with a water level. Then curves that represent the return period or related to the risk to the dam are estimated. The events that reach the same water level are in the same curve, and the events that reach a lower value are below the curve. Finally, joint return period curves by a Frank copula are estimated. Curves that are related to the probability of the peak value and the volume value are exceeded. Curves that are related to the probability that the peak value or the volume value are exceeded, which is the primary return period, and the curves that are related to the probability that an event with a primary return period bigger than a threshold occurs, that is the secondary return period. These figures provide a lot of information as each kind of joint return period are compared with the curves that represent the risk to the dam. As an example, an event has been chosen. This event has a copula value of 0.9, and the return period associated with the risk to the dam is 31 years. Then the following return periods are, in the case of the firstly considered return period, is 137 years. In the case of the primary return period is 10 years, and in the case of the secondary period is 23 years. Then the most similar joint return period to the return period related to the risk to the dam is the secondary return period, although they are not equal. And they are similar because they are being calculated in an analogous way. The secondary return period can be seen as the probability, as the time elapsed between two successive events exceeding a copula value, and the return period linked to the risk to the dam is the time elapsed between two successive events exceeding a water level. In conclusion, a methodology to compare the probability of occurrence of a flood event with the return period linked to the risk to the dam was developed. For that, synthetic hydrographs were generated by a fan copula and were routed through the reservoir. And the maximum water level reached at the dam was used as a surrogate of its hydrological risk. And then, instead of using the secondary return period, flood hydrographs should be routed to estimate the risk to the dam, as the hydrological risk to the dam is related to the maximum water level reached, and considering that there are differences between return periods. So, the proposed methodology procures useful information in order to estimate the design flood hydrographs. The future work will be evaluate the sensitivity to different reservoir volumes and spillway length. Thank you for your attention.
Thank you. Questions?
Yes. Okay, if you can imagine that there is one flood a year, then of course the maximum flow would correlate with maximum volume. But it isn't like that. So, I mean, one peak can give the maximum peak and another volume. Because of that, of course, the time series, according to maximum annual peak, would differ from the maximum series referring to volume. I mean, to avoid this, it is, I think, the only one possibility, and sorry, I can to refer you to my dissertation from 64 years, I mean to use peak over threshold. Then the volume is counted over threshold, the peak is counted over threshold, and the duration, of course, if so, over threshold. And then you would have, for all these three variables, lower bound 0, and your time series, according to maximum volume, maximum duration, and so would be exactly the same. Then you can follow, and then you can go to annual probability, of course, from that. But starting from all events above threshold. What do you do? What have you done?
I selected the maximum annual peak and the volume of that flood event, and that's a pair.
Okay, thank you. More questions?